and welcome to another discussion on momentum. And today we're going to focus on types of collisions. And after we focus on types of collisions, then we're going to move into this idea of combining types of collisions with conservation of energy. So we have conservation of momentum and conservation of energy type problems where we're going to combine those two types of problems together. What I really like about this unit is this unit really ties in everything that we've covered this semester. So we've covered velocity, we're dealing with velocity, so we're dealing with kinematics, and then we're dealing with mechanics, we're dealing with forces and how do forces affect motion and how do forces affect the momentum of an object. So the first thing that we're going to do is we're going to look at a couple of different types of collisions. So three different types of collisions that we're looking at is we're looking at elastic collisions, and we're looking at inelastic collisions, and then we're talking about either completely or perfectly inelastic collisions. So that's elastic collisions, inelastic collisions, and perfectly inelastic collisions. Okay. And in this case, what we're going to do is we want to think first elastic versus inelastic. And when I think off the top of my head, when I think elasticity, I would think like bouncing off of things, whereas inelastic would be like sticking together. Okay. And so we're going to look at those different examples. And what does that have to do with energy as well? So elastic collisions, linear momentum is conserved, but linear momentum is always conserved. Also, your total energy is conserved. But what is going to end up being different is that your total kinetic energy is conserved. So you have the same kinetic energy before as the kinetic energy after. And the example that I use, and I used this example last year in chemistry, if you had my class for chemistry, but when we're talking about gas particles and the way gas particles are moving, when gas particles are moving through space, they're moving super quick. And one part of our kinetic molecular theory is that collisions between gas particles are considered to be perfectly elastic. And the reason that we state that is because we want it to be very clear that when those collisions happen between the gas particles of ideal gas particles, that kinetic energy is conserved. So we're not changing that kinetic energy, we're not losing kinetic energy. Okay, so therefore, it's important for us to know that velocity of object A plus the final velocity of object A is equal to the velocity of object B plus the final velocity of object B. So this type of problem, the way that this is written out, might look a little bit different than something that you're used to. So another way to write that would be VA plus VA final is equal to VB plus VB final. Okay. And you can actually derive that equation. It's derived in the chapter in Giancoli that you're working through right now. So I would really spend a little bit of time when you're doing your reading to look at the derivation of that and how we end up getting that. Okay. Now, when we're looking at inelastic collisions, linear momentum is still conserved. Total energy is conserved because those are our laws of conservation, but our kinetic energy is not conserved. So our kinetic energy initial is not equal to our kinetic energy final. And that's how we can determine if a collision is elastic or if it is an inelastic collision. So if we look at the kinetic energy before and we look at the kinetic energy afterwards, and those two are not the same values, then we know that this would be an inelastic collision. If they are the same values, then we know that it's a perfectly elastic collision. So explosions. Explosions are another type of collision that's an inelastic collision. So explosions are going to be where you're starting with a momentum of zero, but you're also starting with a kinetic energy of zero, right? And you don't end with a kinetic energy of zero. Think about the last time you watched fireworks, okay? When you watch fireworks, you see that explosion. You can see the particles explode and move out, right? So you can see the velocity of those particles. The kinetic energy of those particles is not equal to zero. So we know that in explosions, our kinetic energy is not conserved. Okay. So explosions are inelastic collisions in reverse. Okay, so here's another example of conservation of momentum. Whenever two objects collide or when they exert forces on each other without colliding, such as gravity, momentum of the system of both objects together is conserved. This means that the total momentum of the object is the same before and after the collision. So we have our momentum before is equal to m1v1 minus m2v2. And the reason it's minus is because V2 is going the opposite direction. If they were going the same direction, then fine, it's going to be plus, okay? Now, in this case, when these two objects collide, they go opposite directions. So now you have the momentum after is negative m1va, or the velocity of object 1 final, and then plus m2vb, or the velocity of object 2 final. Okay, so when we combine those, when we look at those, we know that the momentum before is equal to the momentum afterwards. The momentum before is equal to the momentum afterwards. Okay, so here's an example. If I fire a rifle, okay, I fire a bullet and the bullet is shot into a giant slab of butter on a frictionless surface. Okay, frictionless surface. So we know that we're not going to take into consideration the fact that work is going to be done by friction. Okay, so we have our bullet over here and our bullet is shot to our butter. Okay, now so the rifle of the bullet into the giant slab of butter on a frictionless surface. The bullet penetrates the butter, but while passing through it, the bullet pushes the butter to the left and the butter pushes the bullet just as hard to the right, slowing the bullet down. If the butter skids off at 4 centimeters per second after the bullet passes through it, what is the final speed of the bullet? Okay, so we need to look at the before situation. So our before situation, okay, is going to be right here. So we're going to have our momentum of our bullet and our velocity of our bullet plus 0 because our butter is not moving. Okay, and down here, we're going to have our momentum of our bullet, velocity of our bullet, plus the momentum of our butter times the velocity of our butter, okay? So when we look at that, we set up our before and our after table. So our bullet is our 0.035 kilograms, okay? And then we have 700 meters per second. That's how fast the bullet is going. The butter has a momentum of 0 in the beginning, okay? And then in the end, we have 0.035 times the velocity of the bullet and plus 7 times 0.04. So when we do the calculation, we get 24.5 plus 0 is equal to 0.035 V plus 0.28. So I bring the 0.28 to the other side of my equation by subtracting both sides by 0.28, and then I divide by 0.035, and I get that the velocity of my bullet in the end is 692 meters per second. So the butter does slow down the bullet, but it doesn't slow down the bullet perfectly, obviously, okay? So let's look at some of your in-class practice problems. Here I have a 300-gram block is sliding to the right across a frictionless floor at 4 meters per second. When it collides head-on with a 200-gram block that is sliding to the left at 3 meters per second. After the collision, the 300-gram block is moving back to the left at a speed of 0.5 meters per second. So it's really important for you to be able to pay attention to, we have our right and we have our left. So our right, I'm going to make as our positive velocity, and our left, I'm going to make as our negative velocity, okay? So I'm going to go ahead and set up my before and after table, okay? So before, I have my 300-gram block, okay? And I have my 200-gram block. And then I have my totals. So my momentum of my 300-gram block is 300 grams times 4 meters per second. Okay. And then my momentum of my 200-gram block times negative 3 meters per second. Okay. And the reason I'm able to keep it in grams here is because my grams are going to end up canceling on both sides of my calculation. Okay. So I don't even need to go ahead and I don't even need to worry about that. So afterwards, I have my 300 gram block. And my 300 gram block is moving to the left, so negative at 0.5 meters per second. And then my 200 gram block, we're not sure what the velocity is. So when I go ahead and add those together, I end up getting 1200 right here. So I have 1200 minus 600 is equal to 150, or sorry, negative 150 plus 200 V. Okay. And when I go ahead and manipulate that equation, I get 600 and then add the 150. So I get 750 kilograms times meters per second is equal to 200 kilograms times velocity. So I divide both sides by 200 and I end up getting that my final velocity is equal to 3.75 meters per second. So my next question is, was the collision elastic or inelastic? So when I was new at doing these problems, I would always look at these problems and go, oh, well, they bounce off of each other. They don't stick together. So it's got to be elastic. But you need to remember, you can only classify something as being elastic if kinetic energy is conserved. So we need to look at our kinetic energy. Our kinetic energy initial is equal to 1/2 mv squared. So 1/2 300, but we can't keep it at 300. We have to do 0.3, okay? Because when you're dealing with kinetic energy, you're dealing with kilograms. And then v squared. So 4 meters per second squared plus 1/2 0.200 negative 3 squared. That's going to end up giving me a kinetic energy of 3.3 joules. Okay. Now my kinetic energy final, I'm going to do 1/2 0.300 times 0.5 squared, negative 0.5 squared, but it doesn't matter in this case, plus 1/2 0.200 times 3.75 meters per second squared. And that is going to end up giving me an energy in the end of negative 1.44 joules. So obviously, if you compare these are not the same. Because they are not the same, kinetic energy is not conserved. Therefore, this is an inelastic collision. Okay, so elastic versus inelastic, you determine the difference between the two based on if kinetic energy is conserved. So now in this case, we have a 6.2 gram bullet is fired at 775 meters per second into a hanging 3.1 kilogram block of wood that acts as a ballistic pendulum. So this is where we're really going to take our notes on ballistic pendulums. So what is a ballistic pendulum? A ballistic pendulum is something that when it's hit, it flies up and it acts as a pendulum. So it moves back and forth. Okay. So I have something hanging here, a block hanging here, and I have a bullet fired to that block. Okay. And that bullet, the mass of the bullet is 0.0062 kilograms. And the velocity of the bullet is equal to 775 meters per second. Now, over here, I have a mass of wood, and that's 3.1 kilograms. Okay. but it is not moving at first. So the velocity of the wood initial is 0. But what ends up happening is the bullet comes in, okay? So it's going in and it ends up embedding itself into this block. And what's it going to do? Well, it's going to cause this block to swing up, okay? And it's going to cause it to swing up like this. And we can figure out what that new height is of that box, okay? We can figure out what the height is. And then when we figure out the height, then we can figure out what the angle is here. So we know that this is 23 centimeters. We know that this is 23 centimeters, okay? And we're going to figure out right here, we're going to figure out what the length of this part of this triangle is, because we figure out that this part of the triangle is the height at which the block goes up. Okay, so let's talk about it in terms of momentum and energy. We have two parts to this problem. Part one, we're going to use conservation of momentum. Conservation of momentum. Okay, and we know that the mass of the bullet plus the velocity of the bullet, or times the velocity of the bullet, plus 0 is equal to the mass of the bullet plus the wood times the velocity of the bullet plus the wood, okay? And it's because it embeds in there, okay? So we end up getting 0.0062 kilograms times 775 meters per second is equal to the mass of the wood plus the mass of the bullet. So it's going to be 3.1062 kilograms times the velocity of the bullet plus the wood. Okay. So what is this telling us? Well, what this is telling us is this is going to help us figure out, well, how fast is that block going before it starts to rise? So think about a roller coaster and you're at the bottom of a hill on a roller coaster. You want to know how high that roller coaster can go based on what that velocity is at the bottom, right? So same thing with this pendulum. We can figure out how high it's going to go based on the velocity at the minimum height, at the height that we have set as 0. So here we end up finding that the velocity of the bullet plus the wood is equal to 1.547 meters per second. Okay, now I have another part. I have not solved my problem completely because I have part 2. And part 2, we're going to use conservation of energy. So in this case, we have, and if you're still at the point where you have to look at your total energy initial equals your total energy final and split that up into gravitational plus kinetic energy initial equals gravitation final plus kinetic energy final, go ahead and write that down, okay? But what I know, at the bottom, we don't have potential energy. And at the top, all of our kinetic energy has run into gravitational potential energy. So we end up having 1/2 mv bullet plus wood is equal to mgh of the bullet plus the wood. Well, our mass ends up canceling because our mass is the same on both sides. So I end up getting, and that's 1/2 mv squared, okay? So I end up getting that my height is equal to v squared divided by 2g. 1.547, square that, divided by 2 times 9.8. And I got that 1.547 from right over here on the left-hand side where I found the velocity of the bullet plus the wood, okay? That's going to end up giving me a height of 12.2 centimeters. So I know it goes 12.2 centimeters high. Okay, so when I figure out the length here, okay, the length of the pendulum minus the height, okay, is that one side, is that adjacent side, divided by the hypotenuse, which is the length again, okay, is equal to cosine theta. So theta is equal to inverse cosine length, which is 23, minus 12.2 divided by 23. And I end up getting that my pendulum makes an angle of 62 degrees. Okay. So moving to the next question, and you'll notice all of these questions have to do with laws of conservation. Okay, so this next question says, a block of mass M is released from rest to slide down a smooth ramp, so friction is negligible, or we don't include friction. The block's initial height above ground level is called h, okay, and it's labeled in the diagram below. At the bottom of the ramp, the block slides across a smooth, flat ground. So the smooth, flat ground is telling us that there's not friction slowing it down. There are no frictional forces acting against us, until it runs into a larger block of mass 2m that is initially at rest. So this is important, and that's important. So we have mass m is released from rest, okay, to slide down. It then hits 2m. What we're being asked, it says the first object stops. So the first object stops due to the collision, and the larger block slides up a second smooth ramp. Find the maximum height for 2m. That's what we're looking for. What is the maximum height? So we want to figure out what is this height. We'll call that h final, okay? So I need to break this up into sections. My very first section is going to be right here, okay? And part one, so this is part one, and part one is going to be conservation of energy because there's no collision yet, okay? Then when this block gets down here, I have my M. Here, right here, I have part two. And part two is going to be conservation of momentum. And then block M stands still and 2M comes up this hill. Okay, and so then this part right here, part 3, is conservation of energy. Okay, so obviously these problems take a lot of patience and time, and they're very methodical. So for you to be able to work them out, it's really important for you to be able to explain what's happening in each step. So what's happening in part 1? Well, part 1, I have block M is starting at the top of the hill. So block M has potential energy. Okay, and all of that potential energy is converted into kinetic energy. And we're going to call that V1 squared. Okay, so at the very bottom of the hill, before it hits 2m, it has a velocity. What is that velocity equal to? Well, that velocity 1 is equal to the square root of 2gh. Okay, and I know you don't love using these problems with the variables, but it's really important for you to be able to use them and solve them, because if you can solve variable problems, you can solve any problem. If you can only solve number problems, you can only solve one problem at a time. Okay, so part two now is going to be a collision. Okay, that's our collision. Okay, so part 1 was the falling of our block. Okay, part 2 is our collision. Okay, and so we have block M and velocity 1 plus 0. And why is it 0? Because 2m is not moving, is equal to 0. Hold on a second. Where's the 0 there? The 0 comes from the fact that it says the first object stops due to the collision. So its momentum now is 0 plus the momentum of the new block. So the momentum of the new block is 2m, and we'll call this V2. Okay? Well, our m's are going to end up canceling, and we end up getting that V2 is equal to V1 divided by 2. So that's equal to the square root of 2G capital H divided by 2. Okay? So then you end up having part 3. Part 3 is the rise of 2m. So 2m starts with kinetic energy. 1/2 2m, because that's the mass of it, 1/2 m, and then v squared. So square root of 2gh over 2, and I'm going to square that, is equal to m, which is, in this case, 2m, gh final. Okay? So my 2m cancels on both sides. And when I square everything, I get 1/2 2gh divided by 4. So my 2's cancel here, and I get GHF. So then my G's are going to end up canceling. So I get HF is equal to H divided by 4. Or it goes 1/4 as high as block M started. And think about it. Does that make sense? Well, yeah, you're converting the energy into a more massive object. So it's going to cause the more massive object to not go as high, right? Because the more massive object has more inertia, it has more resistance to change in momentum. So it should make a little bit of sense to you. Now, in this case, I have a 3-kilogram bowling ball and a 7-kilogram bowling ball. They're hung from equal length cords right next to each other, as shown in the diagram below. The 3-kilogram ball is pulled back from its equilibrium position to some starting height H initial, and then released from rest to swing down and collide with the 7-kilogram ball, which is initially at rest. Immediately after the collision, you have the 7-kilogram ball swings at 1.3 meters per second, and the 3-kilogram ball has reversed direction and swings 0.8 meters per second. Find the height initial from which the 3-kilogram ball was released. Okay, so let's look at that. We have this is a 2-part problem. Okay, part 1, you have it's falling. Part 1 is falling. And so you're dealing with conservation of momentum, or I'm sorry, conservation of energy. Okay, you have mgh initial is equal to 1/2 mv squared. Okay, and we'll call that v3 because it's the velocity of the object 3. Okay, so we know that the mass cancels, okay, and we know GH initial equals 1/2 V3 squared. And we're trying to find H initial, okay? So let's look a little bit further into that. What are we going to do? Well, we need to do part 2 first. So you figure out what your parts are, and then you go, okay, where do I start? Well, part 2 is a collision problem. Okay, so you have object 3 times the velocity, and we're going to call that velocity of object 3, plus 0. And why is that 0? Because the 7-kilogram bowling ball is hung, and it says that the 7-kilogram ball is initially at rest. So that's going to give you your 0. And that's going to end up equaling your mass of 3 times your velocity, which I'm going to go ahead and plug in as negative 0.8 meters per second, plus the mass of object 7, so mass 7 times the velocity, and we determined the velocity was 1.3 meters per second. Okay, so we end up having 3 V3 is equal to 3 times 0.8, negative 0.8, don't forget that, plus 7 times 1.3. And when we do that calculation, we end up finding that our velocity there is equal to 2.23 meters per second. And that's our velocity 3. So now I can take this velocity and I can plug it in right here. So I end up getting my H initial is equal to V3 squared divided by 2G. So 2.23 squared divided by 2 times 9.8. Okay, and that's going to end up giving me that my height is equal to 0.254 meters. Okay, and that's what the question asked. It said, find the initial height from which the 3-kilogram ball was released. Okay, so our next question is a conceptual question. It's a very conceptual question. In this case, there are no numbers, okay? And most of you hate these types of problems, but it's really important for you to be able to think through these problems. It says a large disc on frictionless ice is used in 2 separate trials of an experiment. So think about you're on an ice skating rink, okay? And you've got a disc. In each trial, a puck is sent sliding towards the disc. So we have the puck, okay? And our puck is sent sliding towards our disc, okay? And it says that the pucks are identical in size and mass, but are made of different materials. Because something that's really important in science is understanding that when objects are composed of different materials, they're going to behave differently in space, okay? So what happens is in the first trial, puck A rebounds backwards. So puck A is going this way, okay? This is before the collision. And then after the collision, puck A is going this way, and that's the disc. So this is puck A, okay? Now, in the second trial, puck B stops entirely after the collision, okay? Type B or puck B stops entirely after the collision. And in both collisions, your disc is going to end up moving, okay? So then in this case, you have B. B is going this way. This is before. And then afterwards, B has no momentum anymore, and the disc is moving, okay? It says, in which trial does the disc move faster after the collision? So we need to think about the laws of conservation. So the sum of momentum initial is equal to the sum of momentum final in both cases. So in the first case, or in both cases, no matter what, you have the mass of the puck times the velocity of the puck initial is equal to the mass of the puck times the velocity of the puck final plus the mass of the disc times the velocity of the disc final, okay? And so when we look at that, we end up getting the mass of the puck, if we bring these to the same side, is the velocity of the puck initial minus the velocity of the puck final. And that's equal to the mass of the disc, velocity of the disc, okay? So your change in momentum for your disc is equal to the negative of the change in momentum for the puck, okay? And so that's because if I multiplied this by negative, I end up getting V final minus V initial if I multiply it by negative. And that's the same as change in V, okay? And so then that ends up giving us the change in momentum. So in this case, if we look at this, because puck A has a larger change in momentum because you have a velocity before, you have a positive velocity here, Okay. And then you have a negative velocity here, no matter what that velocity is. Your final is negative. So negative V minus V. Okay. You're going to have a much larger change in momentum there. So because you have a much larger change in momentum for puck A, it causes the disc to move faster with puck A because these are equivalent to each other. Okay. So if you have a larger change in momentum here, you're going to have a larger change in momentum here, a larger change in your momentum here. So larger change in momentum is going to give you a larger change in velocity. Okay. Hopefully that's helpful for you. If you have any questions, go ahead and reach out. You know where to find me. Go ahead and send me an email and I will get back to you and try to help you the best I can.